In this lesson, we discuss unique factorization domains. So we now have all the terminology to define our final class of rings. So we've been studying commutative rings with identity. An integral domain R is called a unique factorization domain. We're going to abbreviate this by UFD, unique factorization domain, if we have two conditions. If every non-zero element call it little r in the ring, which is not a unit, can be written as a product of irreducibles in R. So we can factor every non-zero element that's not a unit into a product of irreducibles. Moreover, the factorization is unique up to associates. So that's the second condition. Factorization into irreducibles is unique up to associates and the order of the factors. So in general, if we can write R as the product of irreducibles P1, P2 up to Pn, and also write R as the product of irreducibles Q1, Q2 up to Qm, then the only way this is possible is if there's actually the same number of factors, m equals n, and each pi is an associate of one of the q's. So for some qj. So now we're going to study some properties of unique factorization domains. Let's look at a couple of examples though. A field F is trivially a unique factorization domain. Since we have this condition on every non-zero element which is not a unit, well, every non-zero element of a field F is a unit. So just by default, a field F is a UFD since every non-zero element is a unit. And the main part of this lesson will be to prove that every principal ideal domain is a unique factorization domain. So we will prove that every PID is also a unique factorization domain. Let's give us some more examples. So in particular, the ring of integers is going to be a unique factorization domain, and we proved that for any field f, that the polynomial ring f adjoint x is a PID. So therefore, so these two rings are therefore going to be unique factorization domains. So now, before we prove that every PID is a UFD, we need to prove the following lemma. In a PID, any ascending chain so these are a chain of ideals, so I1 is contained in ideal I2, and so on, and we have this chain of ideals, and these are all ideals of PID R. In a PID, this chain of ideals must be finite in length. So we can't have an infinite chain of ascending ideals. So what that means is eventually there's going to be some integer n such that every ideal ik will just be equal to in for all k greater than or equal to n. So you say that the ascending chain stabilizes or just is in finite length. After a while, all these ideals are going to be the same. So we'll use this lemma to prove that every PID is a UFD. So let's prove this lemma first. So let's suppose we have this chain of ascending ideals. So let I1 be contained in I2, and so on. And let's assume R is a PID. Then let I be the union of all of these ideals. Now, it can be shown, I'm not going to show all the details, but this ideal I, the set I is actually an ideal. The key idea is that this is an ascending chain, and so I sub 2 is contained in I sub 3, and I sub 3 is contained in I sub 4. That's all you need to show that this is actually an ideal. So since this is an ascending chain, it is straightforward. To show that I is an ideal of R. So since R is a principal ideal domain, this ideal I is principal. So since R is a PID and I is an ideal, we have that I must be the ideal generated by some element A. So then this generator A is an element of the ideal I, and hence I being the union of the ideals I sub I, A must be contained in a particular ideal, I sub n, for example. So let's say I is contained in I sub n for some n. Then we have the ideal I sub n, which is contained in the union of all these ideals, so this is contained in I. But this equals the ideal generated by A, and since I sub n is an ideal, the ideal generated by A is contained in I sub n. So from this statement we see that I actually equals I sub n, and we see then that I sub n is the last member of this chain. So in any PID, there cannot be an infinite ascending chain of ideals. So now for our main result, every principal ideal domain is a unique factorization domain. Now in particular, we've already shown that every Euclidean domain is a PID, so therefore every Euclidean domain is also a UFD. Every Euclidean domain is a UFD as well. So as I just mentioned, the second statement follows from the first. Since we proved already that every Euclidean domain is a principal ideal domain. So now to show that every PID is a UFD, let's let R be a PID, and let's take a little element R which is non-zero and not a unit. So we need to show that little r is the product of irreducibles in R, and secondly we need to show that the factorization is unique. So first, we show that R is a product of irreducibles and second, we will show that the decomposition is unique up to associates. So let's begin. So now if R is already irreducible, then we're done. Because we just write R as the product with only one factor, we just write it as the product of itself. So if not, if R is not irreducible, then R can be factored. By definition of reducible, we could factor R and let's write it as R1 times R2, where neither R1 nor R2 is a unit. So again, if both R1 and R2 are irreducibles, and again, we are done. Otherwise, we know that at least one of these factors, R1 or R2, is reducible, and then we could continue this process of factoring. So otherwise, at least one of these two elements is reducible. So let's say R1 is reducible. Well, then we could factor R1. So R1 equals R11 times R12, where again these elements are not units. So we see that we can continue this process, and we'll show that this process has to stop after a finite number of terms. So if we continue this way, we will obtain a sequence of factors these factors that are not units. So we started out with R, and then we had a factor R1, and then we had another factor R11, and we could continue this process. But this sequence of factors that are not units produces an ascending chain of ideals. So the ideal generated by R is properly contained in the ideal generated by R1. This is because R1 times R2 equaled R, and R2 was not a unit. Neither R1 nor R2 was a unit. And likewise, this ideal is properly contained in the ideal generated by R11. And we continue this process, but all of these ideals are properly contained in the ring R. And now this is where we're going to use the previous lemma. So we have this ascending chain of ideals in a PID. So by the previous lemma, this chain must have finite length. But that means that the factorization must terminate, and therefore we'll end up with a product of irreducible elements. So thus the factorization process of R must terminate after a finite number of steps, and therefore we can conclude that every non-zero element of R that is not a unit can be factored into a product of irreducibles. So now we know that we can factor every non-zero element that's not a unit into irreducibles. We need to show that the factorization is essentially unique. So we must now show that the above factorization is essentially unique. So let's suppose we have R as a product of, as two different products of irreducibles. So let's suppose R equals a product of irreducibles P1, P2, up to Pn. And let's say this equals Q1, Q2, up to Qm. Further, we're going to assume that m is greater than or equal to n. And all the p's and all the q's are irreducible. Then looking at this equation, we see that P1 divides the right-hand side. So it divides the product on the right. And recall that we're in a principal ideal domain. We have proved earlier that every irreducible element of a PID is also a prime element. So since irreducible elements of a PID are also prime, and we know that P1 divides the product on the right, so therefore, since P1 is prime, P1 must divide one of the factors Qi on the right. So we know P1 must divide some factor of the right hand side. Now we could just renumber the factors, and since it's commutative, we could reorder them so that the factor that P1 divides is actually, we could just call that Q1. So say P1 divides Q1, and we could just renumber if necessary so that P1 divides Q1. But now P1 and Q1 are both irreducibles, so the only way that P1 could divide Q1 is if Q1 equals P1 times some unit. So let's say U is a unit of R. So thus P1 and Q1 are associates by definition. They differ by a unit. And since we're working in an integral domain, we can still cancel. We have a cancellation property. So by cancellation, this is again valid because this is an integral domain. We obtain the following equation. So now we'll have P2, P3 up to Pn. This would equal the unit U times Q2, Q3 up to Qm. And then I'm going to absorb this unit U in with the factor Q2 and just kind of relabel these irreducible elements. So I'm going to call it Q2 prime, Q3 up to Qm. Again, where Q2 prime just equals the irreducible element Q2 times U. So this is still irreducible. So now we have this product P2 up to Pn equal to Q2 prime up to Qm, and we can continue this process of canceling each factor of on the left-hand side. All the p's would cancel in the same fashion because they're prime elements. They divide the product on the right, so they must divide one of the q's, and so we could cancel. And eventually, we're going to cancel all of the p's, and the only thing that would be left on the left-hand side would be 1. Well, we couldn't have any q's left over on the right-hand side because those are not units. And so you can't have a product of the q's equal to the unit, the identity 1, because otherwise the q's would be units as well. So that's summarize the last part of this theorem. So let's continue to cancel these p's. So we could continue this cancellation process until all the p's are gone, and we are left with only the identity 1 on the left side, but since the q's are all non-units, once we've canceled the last p, then all of the q's must have been canceled as well. So there can't be any q's remaining. On the right side, you can't have a bunch of products of non-units be equal to the identity, because that would prove that they're actually units. So once all the p's are canceled, we see that all the q's are canceled, and all we have on the right hand side are some units. So therefore, we must have had the same amount of factors on the left hand side and the right hand side. So therefore, m equals n, and then after renumbering, we see that each pi is an associate of factor qi. So we're in a commutative ring, so we can just rearrange and renumber these factors q, the q factors. So this shows that every PID is a UFD. So this theorem was actually inspired by the fact that the ring of integers is a unique factorization domain. But we actually have proven this as a corollary. So this corollary is actually known as the fundamental theorem of arithmetic. So in our terminology, we say that the ring of integers is a unique factorization domain, since the ring of integers is a PID and is therefore a unique factorization domain. So in non-abstract algebra terminology, we know this as saying that every integer n greater than 1 can be factored uniquely into the product of primes. That's usually the way the fundamental theorem of arithmetic is described. There's one more theorem about UFDs that I'm going to mention, but I'm not going to actually prove. The proof is in our text. If R is a UFD, so if ring R is a unique factorization domain, then the ring of polynomials with coefficients in R is also a UFD. So to see the proof, you can see the text. So in particular, we know that the ring of integers is a UFD. So the ring of polynomials with integer coefficients is therefore a unique factorization domain. But recall, we've actually proven that the ring of polynomials with integer coefficients is not a PID. So the point is that we've just shown that every PID is a UFD, but the converse is not true. Not every unique factorization domain is a principal ideal domain. So the class of unique factorization domains is actually bigger than the class of principal ideal domains. So now we end our discussion of unique factorization domains by describing the irreducible elements in the ring of Gaussian integers. So we're going to talk about the factorization of Gaussian integers. So that's the ring Z adjoin I. So we know that the Gaussian integers, the ring of Gaussian integers, is the Euclidean domain. And hence it's a principal ideal domain and therefore a unique factorization domain. So we can factor the Gaussian integers into irreducibles, but every irreducible in a PID is also a prime element of that PID. So these irreducible elements or prime elements in the Gaussian integers are called the Gaussian primes. So an irreducible element or a prime element in the ring of Gaussian integers is called a Gaussian prime. So we're going to use the norm on the Gaussian integers to identify the Gaussian primes. So recall that for any element a plus bi, it's a Gaussian integer, we have the norm of a plus bi that's going to equal a plus bi times its complex conjugate a minus bi, and so we get a squared plus b squared. So now let's look at an element, let's say alpha. Let alpha be a Gaussian integer whose norm is a prime P in the ring of integers. So now if I could factor alpha as beta times gamma, then as integers we have P equals the norm of alpha, which equals the norm of beta times the norm of gamma, because the norm is multiplicative. So since these are all integers, we know that P does not factor in the integers. So 1 of norm of beta or norm of gamma must be equal to 1. So one of norm beta or norm gamma must equal 1, and the other must be equal to p. Well, we already know that the elements that have norm equal to 1, so we have shown that the only elements with norm 1 are the units in this ring, plus or minus 1 and plus or minus I. So we see that if norm of alpha is a prime in the ring of integers, then if I could factor alpha, one of the factors must be a unit. So therefore, alpha is an irreducible element in the Gaussian integers. So that's the same, again, as saying that alpha is a Gaussian prime. So anytime you have an element of the Gaussian primes whose norm is equal to a prime in the integers, then that element is irreducible, and we call that a Gaussian prime. So for example, the Gaussian integer 2 plus I is a Gaussian prime since the norm of 2 plus I would be equal to 2 squared plus 1 squared, which is 5. Now let's look at the norm again. We know that the norm of a plus bi would equal a squared plus b squared, but it's also equal to the product a plus bi times a minus bi, the product of these conjugates. So if a prime p in the integers equals a squared plus b squared for some integers a and b, then this equation actually produces a factorization of the prime p in the ring of Gaussian integers. And we can factor p into irreducibles in the Gaussian integers, and we could factor p as a plus bi times a minus bi. So the prime numbers in the integers are not necessarily prime in the ring of Gaussian integers. So now we're going to look at which primes can be written as the sum of the squares of two integers. This is what we're going to address. So which primes can be written in the form a squared plus b squared? Well, the smallest prime number 2 can be written in this form. So 2, we can write that as 1 squared plus 1 squared. And hence we could write 2 as 1 plus I times 1 minus I. Now these factors, 1 plus I and 1 minus I, are actually associates. And to see this, let me factor out a negative I from the second factor. So this would leave a factor of 1 plus I. So factor out a negative I. And so we see that 2 can be written as negative I times 1 plus I, the quantity squared. And so we see that 1 plus I is an irreducible element in the Gaussian integers. So now we're going to see that any prime that is congruent to 3 mod 4 cannot be written in this form, a squared plus b squared. So any integer, in general, any integer, not just primes, any integer squared is 0 or 1 mod 4. So an even integer, when you square it, would be divisible by 4, so it would be 0 mod 4. And any odd number, any odd integer, when you square it, will be congruent to 1 mod 4. So if we look at the quantity a squared plus b squared, if a and b are both even, then this sum, a squared plus b squared, would be 0 mod 4. If one was even and one was odd, this term would be 1 mod 4. And if they're both odd, this would be equal to 2 mod 4. So this expression, a squared plus b squared, is either 0, 1, or 2 mod 4. The point is, it can never equal 3 mod 4. So thus, any prime p, which is congruent to 3 mod 4, so primes like the number 3 or the number 7, these primes, any prime p that's 3 mod 4, is not the sum of two squares of integers, and hence p cannot be factored in the ring of Gaussian integers. And so hence p remains a prime in this ring. So p is a Gaussian prime as well. There's actually a theorem proven by Fermat that if p is a prime, in the ring of integers that is 1 mod 4, then it is a fact that p actually can be written as a product, a sum of squares, a squared plus b squared, for some integers a and b. So therefore, the Gaussian primes that is, the irreducible elements in the ring of Gaussian integers, consists of, first, the Gaussian prime 1 plus I, and then any associates. So remember, the units of this ring are plus or minus 1 and plus or minus I. So you could multiply any one of these Gaussian primes by those units and you'd still have an irreducible element. Secondly, any primes of the ring of integers that are congruent to 3 mod 4. So these primes remain irreducible in the ring of Gaussian integers. So for example, primes like 3, 7, 11, 19. So these primes remain prime in this ring. And thirdly, any elements a plus bi and their conjugates a minus bi, which are distinct irreducible factors of a prime p, which can be written as a squared plus b squared, for primes p in integers with p congruent to 1 mod 4. These are all of the Gaussian primes, all the irreducible elements in the ring of Gaussian integers. So let's look at an example of factoring into Gaussian primes. So let's factor 33 plus 4i into Gaussian primes. So let's look at the norm of 33 plus 4i. This will equal 33 squared plus 4 squared, which gives us 1105. And let's factor this into primes in the integers. So this factors as 5 times 13 times 17. So if we can find a Gaussian prime with norm equal to 5, then it will be a factor of 33 plus 4i. So the Gaussian primes with norm 5 are 2 plus or minus I and its associates, so we can also have 1 plus or minus 2i. And then Gaussian primes with norm 13 are 3 plus or minus 2i and their associates, so 2 plus or minus 3i. So we can divide 33 plus 4i by one of these factors. So let's divide 33 plus 4i by 2 plus I. So to divide by a complex number, we actually multiply the numerator and denominator by the complex conjugate and reduce. So 33 plus 4i over 2 plus I, multiply the numerator and denominator by 2 minus I. And so in the numerator we'll get 70 minus 25i divided by 5, which now can be reduced to 14 minus 5i. Now let's take this remaining product, 14 minus 5i, and divide it by one of the Gaussian primes with norm 13, say 3 minus 2i. So again, we multiply the numerator and denominator by the conjugate, which is 3 plus 2i. So we'll get 52 plus 13i divided by 13. So we get 4 plus I. We see that 4 plus I would have norm 17, 4 squared plus 1 squared. So therefore 4 plus I is an irreducible factor of 33 plus 4i as well. So thus we have the following factorization: 33 plus 4i equals 2 plus I times 3 minus 2i times 4 plus I. And this is unique up to associates, and also unique up to the order of the factors. So now that we've finished discussing unique factorization domains, let's give a summary of the various classes of commutative rings with identity. So we have the following chain of containments here for these classes. Fields are properly contained in Euclidean domains. That is, all fields are Euclidean domains, but the converse is not true. And we've proved that every Euclidean domain is also a principal ideal domain. So the class of Euclidean domains is contained in the class of PIDs, and every PID is a unique factorization domain. Prove that in this lecture. And these are all classes of integral domains. So all of these containments are proper Let's look at examples to illustrate this fact. So the ring of integers is a Euclidean domain, but we know that the integers do not form a field. Now we haven't looked at all the details. There's a proof in the textbook that the ring Z adjoin 1 plus the square root of negative 19 all over 2, this is a principal ideal domain that is not a Euclidean domain. Again, see the proof in the book for all the details. And again, it's true that if a ring is a UFD, then the ring of polynomials with coefficients in that UFD is also a UFD. So the ring of polynomials with integer coefficients is a unique factorization domain that we have shown is not a principal ideal domain. And finally, the ring Z adjoint square root of negative 5 is an integral domain that is not a unique factorization domain. So we actually showed that 3 is irreducible in this ring, and 3 divides 9, but we can also write 9 as 2 plus square root of negative 5 times 2 minus square root of negative 5. And since the 3 is irreducible and the factors on the right are both irreducible, we see that factorization is not unique. So see that z adjoint square root of negative 5 is not a unique factorization domain. So this chain of containments summarizes the facts that we have shown over the last few lectures and demonstrates the relationship between the various classes of commutative rings with identity.